Hey, so this time we'll try to apply the Leibniz integral rule, which basically I proved in my previous two videos. So I gave a detailed proof of that. So this time I'm going to put that into a good use to derive something called as the gamma function. Okay, so let's do that. Okay, to start with, so we have an integral here on the board. So this particular integral, so it's 0 to infinite e to the power minus tx dx. So what we'll do is we'll try to differentiate this. Before that, we'll try to evaluate this, and then we'll differentiate it to arrive at the gamma function, okay? Okay, so now what I'm going to do is I'm going to evaluate this. So for that, I'm going to change the variable y, which is basically tx. Okay, so I'm going to do this. So this is integral e to the power minus y, and now your dx will change. So that's basically dy is t dx. So dx is 1 by t dy. Okay, now your limits will change. So for when your x is 0, y will be 0. When your x is infinite, y is infinite, right? Now this is 1 by t integral 0 to infinite e to the power minus y dy. All right. Now this is 1 by t. Now antiderivative of e to the power minus y. This is basically minus e to the power minus y. Okay. Because if you differentiate this, you're going to get e to the power minus y. So now you can apply the limits. So 0 to infinite. So this is going to be 1 by t. So there's a minus sign here, and then e to the power minus infinite is 0 minus e to the power minus 0, which is basically 1. So this will be 1 by t, okay? So you're going to get 1 by t here. And now what I'm going to do is basically, so let's write down what we have here. So f of t is basically integral 0 to infinite e to the power minus tx dx. This is equal to 1 by t, right? Now, what happens if we differentiate this function? So if you differentiate this, it's f prime t. So this is d by dt of this integral 0 to infinite e to the power minus tx dx. And your right hand side will be minus 1 by t squared, so which is basically the derivative of 1 by t. Now, the question is, can you take the derivative inside the integral? And the answer is yes, you can do this because e to the power minus tx, well, you can consider this, and it is a function which is continuous, right? It's continuous maybe in the domain 0 infinite cross 0 infinite. Okay, so this one corresponds to your variable t, this one corresponds to your variable x. Okay, so you're picking values of t from this particular interval and values of x from this particular interval, and this symbol denotes that it's continuous in this particular set here. Okay, so because it's continuous here, and also if you take the partial derivative of this function e to the power minus tx, this is basically minus x e to the power minus tx. Okay, and again, this is going to be, as you can see, this is very good continuous function. Again, it's continuous in the same domain. And so if you look at the statement of the Leibniz integral theorem, because this is continuous and also because the derivative is continuous, you can take the derivative inside the integral, okay? So I can do that, and let's take the derivative inside the integral. So it's basically partial derivative of e to the power minus tx dx. This is going to be minus 1 by t squared. And so the derivative will be 0 to infinite minus x e to the power minus tx dx. Okay, and so this is minus 1 by t squared. And now you can cancel the minus signs, so this will become plus. And so what you have is integral 0 to infinite x e to the power minus tx dx is equal to 1 by t squared. Okay. Now what happens if I differentiate this one more time? So if you differentiate this again, you can take the derivative inside the integral because of the same conditions, because the same conditions are satisfied that this particular function is continuous and its derivative is also continuous. So you can take the derivative inside and now you can differentiate it. Okay. And the right hand side, if you take the derivative, it is minus 2 divided by t to the power 3. And so if you differentiate this, what you have is minus x squared e to the power minus tx dx is equal to minus 2 divided by t to the power 3. So minus and minus, you can just remove it. And so you get this second equation here. So if you compare the first and the second equation, what you see is that the first equation here and second equation here, so what's the difference here? The difference is that you have an x here, this here is x squared, and in your right hand side, this is 1 by t squared, this is 2 divided by t cubed. Okay. Now, the thing is, if you differentiate this one more time, so this will be, again, the derivative goes inside the integral, and this will become minus x cubed e to the power minus tx dx is equal to minus 2 times 3 divided by t to the power 4. Now you can cancel the minus signs, and this is what you get. Okay. Again, what's the difference between second and third? Here there's x to the power 3, and your right hand side is 3 times 2 divided by t to the power 4. So maybe you can write this in a different way. This is 3 factorial divided by t to the power 4. Basically, your factorial is you're multiplying all the numbers starting from that particular number n. So let's say n factorial is n times n minus 1, etc. till 1. So you're multiplying all of them. So that's n factorial. So that's what you get here. So 3 factorial divided by t to the power 4. So if you differentiate this, if you keep differentiating this, the general formula that you get is integral 0 to infinite x to the power n e to the power minus tx dx is equal to n factorial divided by t to the power n plus 1. Now, this is pretty interesting because what I can do here is I can just take the t to the power inside the integral, right? I can just bring it to the left hand side and take it inside the integral, which I get as t to the power n plus 1 x to the power n e to the power minus tx dx is n factorial. That's pretty interesting. Now what I'm going to do is I'm going to change the I'm going to do the change of variables. So y is tx, so dy is t dx. Now I can group t and x here. So this is integral tx to the power n, and then you have a t here, because t to the power n plus 1, you can split it, and you have t to the power n, and then t, and t to the power n and x to the power n can be grouped together like this. And there's this e to the power minus tx, and then there's dx. Now let's put this in terms of y. Okay, so what happens here is that, okay, let me use the eraser here. So tx will become y, right? Because y is tx, and this will again become y, right? This is your y term here, and then t dx is basically dy. So I can just do that. So this is dy. Now I just have to change the limits here. So when your x is 0, y is 0, and when your x is infinite, y is infinite. And so this is equal to n factorial. So I've just done the change of variables here and I get something magical. So let me write this again. So integral 0 to infinite y to the power n e to the power minus y dy is in factorial. Well, this is pretty interesting because this left-hand side is your gamma function. Okay, so this is basically gamma n plus 1. Okay, and that's integral 0 to infinite y to the power n e to the power minus y dy, which is basically n factorial. I should tell you, this is like gamma function. Let me write down the general gamma function. So gamma z is integral 0 to infinite y to the power z minus 1 e to the power minus y dy. Okay, where the real part of z is positive. So your gamma function is basically, as you can see that these two are the almost looking same, right? That's because this version is the generalized version. So you can extend this to complex numbers. So, and this can be defined for complex numbers. So that's what is the gamma function, the bigger gamma function. And here what you see is I'm taking a special or a particular case where your z is n plus 1, right? When your z is n plus 1, you get this. You get this integral. And this is basically n factorial. Okay? Yes, so that's a beautiful application of the Leibniz integral theorem. And yeah, that's it. So because I thought this is pretty interesting, very easy application of the integral theorem. So I just thought maybe why not make a video on that. So if you want to watch my previous two videos on Leibniz integral theorem, maybe you can do that. It will be there in my channel. Yeah, that's it. So thank you so much for staying till the end, and I will see you next time. Bye.